So we were looking at how to find which particular X that this approximation would be less than 0.01. So our approximation for f of X, we're using 1 plus 1/2 X. So first we just kept putting in numbers. We put in 0.4 and we saw that the error was not less than 0.01. We put in 0.3 and we saw that the error was less than 0.1, but that's not real accurate. And when you're doing numerics, we need to be a little bit more accurate than that. So we started looking at the Lagrange, I'm not Lagrange, oh, I'm already ahead of myself. We're looking at the Taylor series approximation. So we went back to here and we said, well, we found the Taylor series approximation to this. I had made a mistake, but I corrected it. So now we know what it is. And so then we came down here and we found that to leading order, this looked like the error between this and what we were taking as its approximation was just this first term. And the reason why we were saying that in general, this first term would be much larger is because when you take a number less than 1, as you cube it and raise it to the 4th, it gets smaller and smaller. So to leading order, this would be the largest value. Okay, so we were here and we were just using this. And so in using this now, we're saying that our error is the absolute value of the square root of 1 plus X minus the approximation 1 plus 1/2 X. And so to leading order, we were saying that that would be the absolute value of 1/8 X squared. And we are forcing it to be less than 0.01 because that's what we wanted from the original problem. Okay, so then that says that X squared becomes less than, and I think I may have had equal to, I'm not sure, but less than, we'll put the equals in there, 0.08. And so then that gives us negative 0.283 is less than or equal to X is less than or equal to 0.283. So now that's even better. That's even a better approximation than what we had before. Before, we said, oh, the number of points, 0.3 worked. Oh, I'm up too high. Here, we said 0.3 worked. But now we can see we can get even smaller, the smallest number. So we can go down. And if we get something that looks like that, our numbers can go as small, 0.3 work, but we can get as small as 0.283 and it will work. Okay. So that was one way of looking at it. All right. Then there's a third way, which is pretty ugly. This is the third answer. And the third answer is to do an algebraic computation. Okay, hi, Yibing. So for an algebraic computation, we're just going to do it brute force. That is, we're not going to use, we're not going to just test numbers. We're not going to do it to leading order. We're actually going to do it brute force. Okay, so that means to actually solve this, solve the inequality. That the absolute value of the square root of 1 plus X minus 1 plus 1/2 X is actually less than or equal to 0.01. So now this is actually just brute force. Okay. And as we do this, this is actually pretty long and drawn out. And it's very difficult to solve it this way. So that's one of the reasons why we use numerics and approximations. This is extremely difficult. It's not extremely difficult. I'll just say this is difficult. Okay. And so if you try to solve this thing, this is what we get. So if we take and we just deal with the left-hand side, because, oh, let me see, what's the left-hand side? I didn't tell you what the left-hand side is. So I end up with negative 0.01 is less than the square root of 1 plus x minus 1 minus 1/2 x is less than 0.01. Okay, so this is doing it by brute force. All right, so if we just do the left-hand side, we end up with negative 0.01 is less than the square root of 1 plus x minus 1 minus 1/2 x. All right. So therefore, I'm going to take and put everything, the square root on one side and everything else on the other side. So I get 1 plus 1/2 x minus 0.01 is going to be less than, and I keep forgetting I do have equals, less than or equal to 0.01. And that's wrong. I want the square root. Okay, now let's simplify that. So we get 1/2 x plus 0.99 is less than or equal to the square root of 1 plus x. So now I can square both sides. And so then I'm going to get 1/2 x squared. I'm sorry, 1/4 x squared. And then I'm going to get 0.99x. And then I'm going to get 0.99 squared is less than or equal to 1 plus x, because I squared both sides. So when I put this together, I get 0.25 x squared minus 0.01x minus 0.0199 is less than or equal to 0. All right. So then what I need to do is use the quadratic formula. To find out when it actually equals 0. Okay, and so you find out that this thing equals 0. So this equation, so you get 0.25x squared minus 0.01x minus 0.0199 is actually equal to 0, implies that x is equal to 0.3028 and then negative 0.2628. And so then, of course, we have to break the world up into intervals. So you will break it up into an interval like this. And I'll put negative 0.2628 here, and I'll put 0.3028 here, and I will find out that the function is actually positive here, it's negative here, and it's positive here. So therefore, my answer to the original problem is that I get the interval negative 0.2628 is less than or equal to x is less than or equal to 0.3028. Okay, so that is algebraically the true answer. Okay, so the first one we did guesses. The second one we did an approximation. The third one we did it actually figuring it out using algebra. And as you can see, our approximation is not too bad when we looked at leading order. We got negative 0.283 is less than, so that was not bad using leading order. So that was pretty good. But this is the actual true value. Okay, and if you do the right-hand side, it yields no solution. So there's no point in writing all that out. Okay. All righty. So now we want, I think, okay, so our next section is C. And this is error propagation. And numerical stability. Now, if we make an error at a particular time step that we're solving our problem, that error goes into the next calculation, and then that error goes into the next calculation. And so we can see that errors will propagate. Okay, so errors can accumulate or what we say propagate because calculations are performed with approximate representations of numbers. When my daughter's doing her homework, they tell her to use 3.14 for pi. Well, if you use 3.14 for pi, then when you square it, pi squared is not completely accurate, and neither is pi cubed. But if you use 8 digits for 3.1459 and then you continue, then when you square it, your approximation is even better. Okay, so we're going to now let W be an arithmetic operation, an arithmetic operation. So what do I mean by that? It can be plus, it can be minus, it can be multiplication, well, plus addition, subtraction, multiplication, or division. All right. So that's the true arithmetic operation. And W star is going to be the computer version of this operation. So when I compute this, so my X true here is the true value. That is equal to the approximate value plus some error. I'm going to call epsilon. So I'm supposed to get 4. I get 3.9 in the computer. My approximate error is 0.1. And then Y true is the true value, but YA is what the computer is carrying, and it has an error, and it's called eta. So the number computed is equal to what the computer has, the computer operation, and Y. So that could be X plus Y, it could be X times Y, it could be X minus Y, it could be X divided by Y, but it's however the computer's doing it. All right. So therefore, the error in the number computed well, how do we figure that out? Well, it should be X true, the true operation W times Y true, minus what we actually get calculated by the computer, which is X approximate times W times Y approximate. All right, so let's figure that out. So we get, we're going to add in a term and subtract off a term. So I'm going to write this as X true, W, Y true, minus X approximate, W, Y approximate. I have to add that term back on. So when I add that term back on, I get X approximate, W, Y approximate. And this one should have a star on it. Minus X approximate, W star, Y approximate. Okay, so notice I added that middle term in there. All right. So this first piece is, so what does the first piece represent? It says, this is what the true value is of me taking X times Y. And then I'm going to subtract off what, if I use the approximate values, and I did the approximate value of X times Y. So this first piece is the propagated error. That's the error in the fact that I used an approximate value. And every time I take and use that value over and over again, it's going to propagate in my solution and create a problem. over here, this over here, well, this is chopping or rounding or chopping error. All right, so why is it rounding or chopping error? Because this is what, if I were to take and compute the multiplication of the approximate value, and then I subtract off how the computer is computing that. So if the computer is chopping, it's going to create a different value for XA and YA when they're multiplied. So, or if it's rounding. So that's the rounding or chopping error. And let's just make sure we note to ourselves that when we take XA and we do W star times YA, this is that floating point error that we get when we were really trying to do XA W YA. Okay, that's the approximation. All right, so now let's look at rounding error. Okay, so rounding error is we're just going to use to true rounding. All right, so that says we already know when we round something that the difference in its error is less than beta over 2 times that value to beta to the minus n. We did that back when we were talking about rounding. So we would get the absolute value of XA WYA minus XA W star YA. Well, that's less than or equal to beta over 2, the absolute value of XA W YA times beta to the minus n, where n is the number of at the number of points in the mantissa that we then round. Okay, to propagated error. Okay, so there's several ways that we can do propagated error. It could be, we can look at multiplication. So I'm going to do that. And then some division errors and addition and subtraction errors. So let's just do multiplication first. So to make life easy, W is just going to be dot multiplication. All right, so we want to determine okay, we're looking at propagated error. So where's propagated error? So here it is. All right, so propagated error says, what is the error if we were to take the true value and multiply minus the approximate value and multiply, okay? So the propagated error would be x true times y true minus xa times ya. All right. So the error in XAYA is as follows. We get X true, YA, I'm sorry, Y true. These are multiplied, minus XA, YA. So now I'm going to take X true, Y true as they are. And now let's go back just a bit. So YA, didn't put it here, but I can now. So YA is simply Y true minus eta. And XA is simply X true. Whoops. Epsilon, epsilon, epsilon. Okay, before I continue, let me make sure you guys are following what I'm doing and not just writing down symbols. Kayla, how you feeling? Are you just writing down symbols or you have an idea of what's going on?
I think I have an idea.
Okay. Yibing?
Yes, but I just don't understand the omega star. What is that?
Okay. So the omega star is how the computer is actually doing the arithmetic. So for example, when we do problems and we're doing everything in base 10, the computer may be doing it in base 8, base 16, and so it's doing a different type of operation. Okay, and it could be rounding, it could be chopping, it could be doing something very different with the actual values of the numbers that we're using.
So for the error in number computed, we have x true, and we have omega is operation time, and y true minus x approximate times omega star and y approximate. So what is the second term?
Okay. So you're talking about this x true omega w, y true minus xa omega star ya. You're talking about that one line.
Yeah.
Okay. Okay, so you're talking about something like this, right?
Yes.
Okay, so let's just suppose that omega is multiplication and omega star is multiplication by the computer with chopping. to 3 digits. Okay, so my X true is 0.1234567. And my Y true is 0.24682. Okay. All right, so that's X true and Y true. Okay.
Yes.
Now, X true W, Y true, okay, is to take this number and multiply it by this number. Okay. Now, X approximate zero 0.123 and Y approximate is 0.123. Now, if I take this thing and I multiply it out, I get so I get 0.03047218. Okay.
Okay.
Now, X approximate, wrong. Y approximate's wrong. X approximate is 123, and Y approximate is 246. So now X approximate, W star, or omega star, Y approximate is going to take 0.123 and multiply it by 0.246. And that number comes out to be 0.0302 58. But it's using chopping. So it's only going to get this, it's only going to get this piece. So it's only going to go 3 digits. So it's going to chop off this last piece. So its value is 0.03. Okay.
Okay.
So the Y, the omega star, W star really is omega. The omega star says only use 3 digits and then chop. So the approximate value takes the true value, chops them to 3 digits, because I can only use the approximate value. Then do the calculation, and the calculation W star says multiply them, but your result can only have 3 digits. That's the difference between the two.
Okay.
That was a great question. I'm glad you asked that. I think that might have, did that make it even more clear for you as well, Kayla?
Yeah.
Yeah.
Yes.
Okay, all right. Okay, so now we said X approximate is X true minus epsilon. Y approximate is Y true minus eta. All right, so when you finish all of this together, you end up with eta times Y true plus, I'm sorry, epsilon times Y true plus eta times X true minus epsilon eta. All right. So that's the true error. Now, what's the relative error then? Then the relative error in my approximate XA, YA. Well, that says take what I was supposed to get. So that is X true, Y true, minus XA, YA, and then divide that by X true, Y true. So that's my relative error. Okay. So let's compute that. So we get X true, Y true, minus, oh, we already figured this out. I don't need to do this again. I figured that out. So that becomes epsilon Y true plus eta X true minus epsilon eta divided by X true, Y true. So therefore I get, the first one is going to give me epsilon over X true. Then I'm going to get plus eta over Y true. And then I'm going to subtract off epsilon eta over X true, Y true. So that's the relative error. So I'm going to keep going. So now I get that the relative error in XAYA well, epsilon is X true minus X approximate. So that's X true minus X approximate. And that is over X true. Eta is Y true minus Y approximate. And that is over Y true. And then I get two other pieces. I get epsilon is X true minus X approximate. Eta is Y true minus Y approximate. And then I'm going to divide by X true, Y true. And I now get a very nice formula. So this is actually equal to the relative error in X true minus the relative error in, I'm sorry, plus the relative error in Y true minus the relative error of X true times the relative error in Y true. Okay. All right, so this is the relative error in XA, YA. Now, if the relative error in X true, okay, I wrote these wrong. Go back. These should be XA, YA, XA, YA. So if the relative error in XA and the relative error in YA are both very, 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 very small, then we can say that the relative error in XA times YA is almost approximately the relative error in XA plus the relative error in YA. Okay, so we started out, so basically the operation we were looking at was multiplication. Okay, so omega equaled multiplication. So if we take and we multiply X true times Y true and we subtract off what the computer's approximation values for XA and YA are, we get that if the relative errors are really, really small, then the relative error in the multiplication of two approximate values is almost equal to just summing up the relative errors in each individual piece. Okay. Let's look at division. So 1 was multiplication. No, yeah, A was multiplication. B is now division. Oh, and I can keep my example right where it is. Okay, so now I'm going to let my omega or my W equal division. So, okay. So now we want to determine the error in XA divided by YA. And here we're assuming YA is not 0. The same way we assumed up top that XA or YA was not 0. Okay, so we're going to look at the propagated error in X true divided by Y true minus XA divided by YA. This is the propagated error. So we get the error in XA divided by YA. Well, that's going to equal X true divided by Y true. And actually, let me try to write it a little differently. I'm going to do X true divided by Y true minus XA divided by YA. And I'm going to do the same thing before. Okay, so when I put in X true divided by Y true minus XA is X true minus epsilon, and Y true is, yes, and YA is Y true minus eta. Okay. All righty. So this equals, so that's Carolyn's candy. So we're going to cross multiply, find a common denominator. So we get X true, Y true minus eta, X true minus X true, Y true plus epsilon, Y true. That whole thing divided by Y true times Y true minus eta. All right, so when we simplify this, the X true, Y trues drop out, and I get minus eta X true over X true YA. I'm sorry, Y true YA, Y true Y approximate. And then I'm going to get plus epsilon, and that is simply over Y approximate. All right, so that is the true error. The fun comes when we look at the relative error, because that's what we care most about. So the relative error and this is in XA divided by YA, is to take the true error and then divide by X true, Y true. So we end up with minus eta X true divided by Y true, Y approximate plus epsilon over Y approximate. And then that whole thing divided by X approximate, Y approximate. So that's the relative error. So now I feel like I skipped a step. Let's go back. I don't want to use that yet. Thank God for erasers. We're just going to write the true definition first. X true, Y true, minus X approximate over Y approximate divided by X true y true. Okay, let's start there. So I'm going to end up with 1 minus x approximate y true divided by y approximate x true. Yeah, let's start there. Okay. So that's going to give me 1 minus, I'm going to add and subtract a term. So I'm going to add in, let me get rid of that. So I already know that I have x approximate y true. But I'm going to add in x true, y true, and subtract it back off. So that's the best part about math. You can always add 0 when you need to. And this is over xa, y true. Okay, so all I did was that. So now I'm going to rearrange it and write this as 1 plus. And in the numerator, the first, this negative term becomes x true, y true, because it's in the, becomes there. And then the other two become negative, which is xa, y true, minus x true, y true. And then I'm going to divide by xa, y true. Almost there. So we get equals. Now we're going to do some simplification. So I'm going to get 1 plus, I'm going to get x true, okay, so in the place of, I'm going to put two things together. So I get x true minus xa. And that's going to be times y true. And that is over x true and ya. And I have one more term, which is y true over ya. All righty. Whew, so we are good. We have this now is 1 plus, this is the relative error in xa. And then that is times y true over ya. This is what I have, but I can't see it right this second. Minus y true over ya times ya over y true divided by ya over y true. Okay, yes, that is correct. That is correct. All I did was put in 1 here. This is 1. Okay. So we get the relative error in XA over YA is equal to YA over Y true plus the relative error in YA minus 1 divided by YA over Y true minus Y true over YA. Nope, Y true over Y true. Tiage, your class is at 1:30 today. Plus 1. So this then becomes the relative error of XA minus, now we're starting to look at something that looks familiar, Y true minus YA over Y true. So we know what that's going to be. Divided by 1 minus Y true minus YA over Y true. Phew. All right, so we finally got there. So therefore, the relative error in XA divided by YA, which is what we were trying to find, is the relative error in XA minus the relative error in YA divided by 1 minus the relative error in YA. And as before, if the relative error in YA is very small, then we get that the relative error in XA over YA becomes approximately equal to the relative error in XA minus the relative error in YA. Okay. So for omega equal to multiplication or division, relative errors do not propagate rapidly. So do addition and subtraction. I'm gonna do them together. I'm just going to use plus minus. Okay, so let me go back here. I had A was multiplication, B is division, C is addition and subtraction. Okay. All righty. So that means our omega is plus or minus. So let's look at the propagated error. In XA plus or minus YA. So the error in XA plus or minus YA, well, that's going to equal X true plus or minus Y true minus XA plus or minus YA. So this becomes XA minus YA, X true. X true minus XA plus or minus Y true minus YA. So that's going to equal epsilon plus or minus eta. So we just get that. All right. So that's just the error in XA plus or minus the error in. So this is simple. This is the true error in XA plus or minus the error in YA. So now let's look at the relative error. So we get the relative error in XA plus or minus YA is equal to X true plus or minus, no, Y true minus XA plus or minus YA. And then that divides by X true plus or minus Y true. And for this, there's no easy formula to actually compute it. Okay. We don't know what it could be. So that's going to come up when we talk about loss of significance of error. Okay. All right. So all of that was looking at propagated error. I have an example. Well, I have an example of rounding error, even though I gave you an example. So I have a couple of examples. I think what I will do is my example, okay, so I already gave you an example of the chopping error. So let me give you an example. Oh, well, no. Here's an example. I'll just finish with this. It's no sense in starting anything. So let's look at rounding error. In XA WYA minus XA W star YA. So remember now, we've been looking at here, we were looking at this was propagated error and chopping. Okay. So the rounding error is the other piece. Let me go back. Yes, so the propagated error was this piece. This was the question that Yi Bing had, which was she didn't understand what XAW star YA was. Okay, so the absolute value of the rounding error is equal to the absolute value of XA omega YA minus XA omega star YA. And we know that the relative error in XA omega YA, well, that's going to equal the absolute value of XA omega YA minus XA omega star YA divided by absolute value of XA omega YA. And that's less than or equal to 1/2 beta to the minus n plus 1. We learned that last lesson. So therefore, we get the absolute value of XA omega YA, minus XA omega star YA is going to be less than or equal to the absolute value of XA omega YA times 1/2 beta to the negative n plus 1. So the example, so here we go. So let's let XA be 0.123 and YA equals 0.567, and omega star is going to be multiplication with 3-digit rounding. Okay, so therefore we get, if we take the true value XA and multiply it by YA, that's use the W, then we get 0.0 0.0694741. And if we do XA with the omega star YA, so now we have 3-digit rounding, we're going to get 0.0697. I think I did the other problem incorrectly, so I have to go back. So the actual error is XA times YA minus XAW star YA. And that is equal to 0.000041. And so if we use the formula for the absolute value of the actual error, it has to be less than or equal to 1/2 beta. I'm sorry, yeah, 1/2 okay, I know, it'll be done. 1/2, I have one more line. The absolute value of XA omega XA times beta to the -3 + 1, because we're using chopping. And this turns out to be 0.000349. So this is indeed less than that. This was predicted. The last one was predicted. Okay, I need to go back just for 1 second, guys, to my example. I circled the wrong thing. If I'm using 3 digits, what did I say it was? Zero, 3, 0, 2. Okay. Okay. Remember, we have to write it times 10 to the minus. So I have to include, so for 3-digit chopping, I would have to include the 2. Okay. So I have to include the 2. All right, that was it. Okay, so I will see you on, oh, yay. Let me not get too excited. I'm taping.